Okay, good afternoon everyone. So my name is Quasi, and today I'm going to be talking about
I'll start again. Good afternoon everyone. My name is Quasi, and today I'm going to be talking about a Quasi-DC potential drop measurement system for materials testing. But before I do, I just should apologize that for some reason on this computer all the fonts have changed and the sizes have changed, so there might be some funny stuff going on, but we'll just see how it goes. So this presentation will be split into a number of different sections. First of all, I'll give some background, of course, to what I mean by this Quasi-DC measurement, before going on to show a series of experiments aimed at demonstrating the advantages of this particular technique, and in particular comparing it to more traditional potential drop methods. And I'll end with showing some of the instrumentation we've developed to be able to do these measurements. So some background. Hopefully many of you will already be reasonably familiar with potential drop measurements, but for the sake of completeness, potential drop measurements are extremely common in a number of different material testing laboratories and may be used for monitoring a number of different damage mechanisms. So fatigue, creep crack growth, gross deformation, for example. The way we take these measurements is that we weld two electrodes to the surface of the component and we inject current between those two electrodes, so that's shown in blue. We then weld another two electrodes onto the surface of the component and we use these to measure the electrical potential. As we know what current we're injecting and we measure the voltage, the potential difference, this gives us our resistance measurement, which is indicative of one of the damage mechanisms that we're looking at. Here is an example, an arbitrary example to illustrate this. This is a creep crack growth test, and we can see that over time the resistance increases, which is indicative of the cracking. So this is what provides us with the information. Traditionally, there are two main ways of doing potential drop measurements. We can either inject a constant DC current through the component, or alternatively we can inject a sinusoidal AC current instead. What this slide kind of summarizes is that both of these traditional approaches have relative pros and cons. So in particular, and I'll go through all of this in much more detail throughout the presentation, but in particular, on the AC side, we see these AC measurements are subject to the skin effect, and I'll show you that sometimes this is useful, but in many cases, we see this can undermine the stability of the measurement. On the other side of these DC measurements are usually considered inherently noisy, and therefore we end up having to inject very high currents, which has all sorts of other problems, particularly practical problems associated with it. Our suggestion, of course, is that we go somewhere in the middle and use what we'll be calling Quasi-DC. So this is extremely low frequency AC, really. So we're using typically something like 0.3 to 30 hertz. So to stress how low frequency that is, of course, if it's 0.3 hertz, it takes 3 seconds to do a full sine wave. And so that's why we're calling it Quasi-DC. It really behaves as if it was DC. And you'll see that this combines all of the advantages to both of these traditional techniques. And throughout the rest of this presentation, I'll kind of go through this table and demonstrating all of these advantages. So I'm going to start off with the skin effect and why that can be problematic for AC measurements. So again, I'm not sure how familiar you are with these approaches, but with AC measurements are subject to what's known as the skin effect. So the current that you inject likes to cling to the surface of the material, and the penetration depth is determined by the skin depth given by this equation. So the amount it likes to cling to the surface is determined by electrical conductivity, the AC frequency, and what's known as the magnetic permeability. So you can see from the equation that the higher the frequency that you inject, the thinner this skin depth becomes and the stronger this effect is. The real problem that we have here is this guy, mu magnetic permeability. The reason this is problematic is because in many materials of interest, particularly ferromagnetic materials, particularly ferromagnetic materials, the magnetic permeability is very unreliable. It will change extremely considerably depending on the temperature, the magnetic history, the material aging, and in particular the stress that you apply. So of course, if this is changing, this effect is changing, this is going to, let's say, undermine the stability of your measurement. And I can show you an example of that. So here we're doing a tensile test. It's a large mild steel component, and we're trying to do an AC potential drop measurement of that. Yeah, you can see that we've got some font issues. We can see that over this period of time, what I'm doing is every 2 hours I increase the stress. So these are all elastic loads. But hopefully you can make out the colors, but at the highest frequency here at 60 Hertz, we see we have very considerable step changes every time we change the load. So what's happening is as you change the elastic stress, you change the magnetic permeability, and therefore you get this change in the skin effect. Clearly, if you're trying to, say, measure the crack length at the same time, but you're having these big step changes in resistance caused by something else, it's clearly going to, as I say, undermine the measurement you're trying to do. On the other hand, if you reduce the frequency all the way down to, say, 1 or 2 hertz, you see we just have this horizontal line here. We're insensitive to these changes in stress. This is, of course, good because this allows us to accurately measure the thing we're actually trying to measure, say, the crack length. So that we can see that by using these very low frequencies that we're able to suppress the skin effect, which is a good thing. The next thing is low noise. And we'll see here that the problem with the DC measurements is that they are inherently noisy. This experiment illustrates that. So this is just a 316 steel block, and again, we're just taking a potential rock resistance measurement of that block. And this time we're not doing anything to it, we're just measuring it over the course of an hour. And we can see that these DC measurements, the conventional approach, we have very considerable noise associated with that. On the other hand, if we're using our Quasi DC technique, these are the red dots here, and probably from where you're sitting, it just looks like a horizontal line. It shows that our noise performance is far, far superior than the traditional DC technique. Is this a fair comparison? No, it is not. In the DC technique, we're using 5 amps, whereas in our Quasi DC technique, we're using only 400 milliamps. So this is by no means a fair comparison, but you'll see we get 13 times better noise performance despite using 150 times less measurement power. Remember, measurement power is current squared, so that's why we get the 150 from that. The reason this is if you think about these DC measurements as just kind of a 0 hertz measurement, then down there at 0 hertz we have a lot of other mess that we need to contend with. We have thermoelectric effects, what's known as flicker noise, and all sorts of other interference. Whereas if we're taking an AC measurement, albeit a very low frequency AC measurement, we can use our electronics to lock into that very specific frequency. It allows us to suppress noise at all other frequencies, and we're only sensitive to that very specific frequency where our signal is. And on top of that, of course, all the electronics that we've been developing to get this very good performance. So we can see that the next good thing is that compared to the DC, we have far better noise performance as well. In this last slide, I was alluding to the fact that because our noise performance is so good, we can get away with using very low power measurements, very low currents. So this illustrates the problem with using very high currents to try to combat it. Usually when we're doing DC PD measurements, we try to combat the poor noise performance by just increasing the current. We try to increase the signal to noise ratio just by increasing the signal. This shows the issue with that. This is infrared thermography of a, again, 316 conventional CT specimen as we put through it more and more current for from 0 to 20 to 30 to 40 amps. And you can see that, of course, as you put more and more current through it, it starts to heat up. You turn your experiment effectively into an electrical heater. All that current that you're putting through the component has to be dissipated some way, and it does this through heat. This is really problematic to us because, of course, as the temperature of the component increases, the resistance is going to go up. So again, we're doing something here that undermines the stability of the measurement. If you compare this instead to you injecting just 300 milliamps, which is typical of what we do, we can see that this resistive dual heating is really negligible, so we don't have this heating of the component that's usually associated with DC measurements. This set of results also reveals another thing of practical importance, and that's this. Here, what you can see here, I don't know if this is clear, but this is the CT specimen, and these are the cables we're using to introduce that current. And you can see that, of course, these are the first things that start to get hot, and in particular where you join that to the component. So in order to accommodate this 20, 30, or 40 amps, which you usually use for DC, you have to use very thick, impractical cables, which you sometimes have to join to a component. Instead, if you're only using hundreds of milliamps, you don't have the same practical issue. Usually what we use is very thin thermocouple lines, which are perfectly good for accommodating hundreds of milliamps. So again, that's a practical advantage to this technique. So I think that's the end of this table. So you can see that we have a methodology which is insensitive to the skin effect, which is an advantage, the main advantage over a conventional AC approach. We can see that it's far less noisy than the DC alternative, which allows us to use much lower power measurements, and with that comes the practical advantage of the small lines and neglecting the resistive heating. I intended to show you some example experiments, but I don't have the time, so I'll just show you an example experiment. And the one I chose is a crude crack growth test, 316H stainless steel, tested at 550 degrees, and of course we just statically load this component. In this experiment, we'll be comparing the conventional DC technique with our Quasi DC measurement, and the first thing to show you is that they are in kind of perfect agreement, as we'd expect. This Quasi DC technique behaves effectively as if it was a DC measurement. The big advantage, however, is if you zoom in on that, you can see the advantage of this improved noise performance. The red dots are the conventional DC approach, the black dots are our new measurement technique. So you can see again the very superior noise performance. In this case, the conventional approach was using 20 amps, here we're using 400 milliamps, so we're getting this greatly improved noise performance, despite in this case using 2,500 times less electrical measurement power. Finally, how we are doing these measurements. Sorry again for the font. It is usually considered extremely difficult to take these extremely low frequency measurements. Usually on commercial equipment, you'll find that it will only go down to, if you're lucky, down to 10 hertz, whereas we're going down to a fraction of a hertz. We've been developing this methodology over the last quite a few number of years, and hopefully, as you have seen through the presentation, we've become quite good at it, and we decided to consolidate all of this experience and expertise into this measurement system. We've designed, I'll try to tone down the sales pitch, but we've designed it so it's highly configurable, and it's quite a complete experimental measurement system with various analog inputs and outputs, thermocouple inputs, and things like this. It's a USB system with the software there already, and it's being commercialized through material monitoring systems, so you can find out more information at that place. So in conclusion, we've developed this Quasi DC measurement system which is insensitive to the problems of the skin effect, it's very low noise, and is therefore very low power, and we've developed the instrumentation which is now becoming available. Thank you very much.
Thank you very much.